Thank you for being here, and thanks to the organizer for having me and providing me with this wonderful opportunity. The title of today's talk is Examples of Resurgence Effects in JT Gravity, the Spectral Form Factor, and Weyl-Petersson volumes. So let me start by telling you what's the plan for today. First of all, I'm gonna give you some motivation for the study of this type of theories and models. And after that, I will review what is the content of the theory of JT gravity and its connection to holography and a particular type of holography with random matrix theory. And after that, I will tell you about the spectral form factor as an important tool to diagnose the discreteness of the energy levels of quantum black holes. And in particular there, we will discover how resurgence can help us to unravel the structure of this observable, and in particular, special realization of the resurgence program, which is called Cheshire Cat resurgence, and that was invented by Gerald here in the audience. And after that, lastly, I'll tell you about how physics can give back something to mathematics in this field, and how both of these different fields can benefit from the exchange of information to one another. And in particular, we will learn how to derive with resurgence some asymptotic formulas for the Weyl-Petersson volumes that I'll tell you about in a moment. So let us begin with the motivation. And basically, JT gravity is a two-dimensional theory of quantum gravity. So the first question that comes up to our mind is, why bothering studying such a theory? They do not describe the universe we live in, and that's correct, but this is not the reason why we study these models, and there are many reasons to do that, gravity. First of all, not every problem that we may want our theory of quantum gravity to solve depend on the dimensionality of space-time. There are some problems that exist in every dimension, as for example, the black hole information paradox. And also the understanding of the black hole microstructures and the microstates of black hole. And so why do we study these problems in two dimensions? Because we have much more control on the theory, and we can perform our computations not only perturbatively, but including also non-perturbative effects, understand whether or not our ideas can solve these issues, and in case they are successful, try to uplift them in higher dimensions. What's more, this theory is also completely solvable and has an holographic duality. So by studying this theory, we hope, and we are doing so, to learn something new about holography and the holographic dictionary. So motivation is clearly holography. And in this context, what's more, JT gravity is also closely related to some system also from condensed matter, which is called the SYK model, which is a model of interacting Majorana fermions, which is a chaotic model. And so by the, let's say, the relation to JT gravity, we can learn something more about the connection between quantum chaos and black hole physics. So the connection between black holes and chaos. In addition to that, also in this theory, we can make sense exactly of what we mean by the quantum gravity path integral. And so we can learn very in depth what are the prediction of quantum gravity in this sense. And if this is not enough, also JT gravity emerges as an effective action when we dimensionally reduce Einstein-Hilbert actions in let's say 4 dimensions, and we consider the near horizon limit of near extremal black holes. So we can also try to understand something about these objects by studying JT gravity and try to learn something, yes indeed, about higher dimensional black holes. So there are probably many other reasons to further investigate these theories, but for the sake of time management, let me stop here. And if there are no questions, without further ado, let me begin the review of the theory. Okay. Basically, JT gravity is the, let's say, the simplest theory of quantum gravity that you can write down in 2 dimensions, not being topological. Meaning that you could start studying a theory with the Einstein-Hilbert action, so something along these lines. But then you would realize pretty quickly that this theory just counts the number of holes and the number of boundaries of the manifold that you're considering. So this is topological. And so what do we do if you want to study a dynamical theory of quantum gravity? Well, you just add a scalar field in the space-time and you couple to the metric in this way. So you had what's called the dilaton with this coupling. And here, what I'm writing down, H is the, let's say, induced metric on the boundary, and K is the trace of the extrinsic curvature. These terms are boundary terms that are meant to make the variational principle well-defined when you're studying your theory. And this -1 is just a counter term that serves to remove some infinities inside this theory. Actually, what we do, we had here some constant phi 0, but we won't bother about this much. So as you can see, the dilaton, basically, if you were to vary this action with respect to it, it would give you some constraint on the scalar curvature, and you would get that the scalar curvature is fixed to be -2. So the space-time is locally hyperbolic, meaning that basically what you have locally is some patches of ADS2. And so you could say, okay, then what's the point of this theory? This seems too simple to be interesting, but it is actually everything but trivial. Since we are not doing this, but if we were to study the equation of motions of the theory, we would discover that actually the solutions are black holes. And so, since in this theory we will be able to exactly quantize it, we will learn something about, for example, the spectrum of quantum black holes. So how to do it? First of all, at this level, without adding any further field in the theory, what the functions that we could study are basically the partition function of the theory, for example. And so we could try to compute the, let's say, the Euclidean path integral of the theory and interpret it as the partition function. So how to do it? Let me write it down. We basically have to path integrate over the fields that we have, so the metric and the dilaton. And here we have e to the 1/16 pi g, and basically this action that I've written up here, plus 2 times the boundary term. Also at the quantum level, you quickly realize that you can path integrate over the dilaton along an imaginary direction and basically obtain from this exponential a delta functional inside the path integral. That imposes basically that you have something like that to include. And all the dynamics is encoded in this boundary term. Well, so now what do? Well, you have to impose suitable boundary conditions to treat this boundary term, and these are Dirichlet boundary conditions. And for self-consistency of the theory, what you have to impose is that the dilaton diverges, let's say, when it approaches the asymptotic boundaries in this way, where epsilon is just a cutoff. It's actually here. Sorry. You're right. Okay, so, and the Euler characteristic of the disk is 1, so it's S0 times 1. What, sorry? Yeah, you're right. I forgot to mention that here I'm just considering the disk contribution. So, yeah, basically I'm considering a manifold with a boundary but with no holes. We will see in a moment that we need actually to include other topologies. So by doing this, yeah, I was saying, and then what you want to impose is that the metric actually goes like this. So basically this is just somehow how your boundary conditions. And if you do this, if you parameterize your boundary curve in this way, let's say, with two functions, f of t and z of t, you discover that only one of them is fundamental, because this z, in order to respect those boundary conditions, has to be expressed in terms of f, and this f is actually the remaining degree of freedom of the theory and what you have to path integrate on. And what you discover after that, you can express your trace of the extrinsic curvature in terms of this f and perform your computations. At the end, what you obtain is the following result. Where is that? This one? Basically, you have a two-dimensional space-time, so you have to parameterize your boundary curve in terms of two variables. One of them, yeah, you're parameterizing the curve. Yeah, yes, thank you. And so what you discover at the end is that basically this path integral reduces to the path integral of a single quantum mechanics with this kind of action. E to the S naught. And here you have to path integrate over f. Actually, it is convenient to express this capital F in terms of a smaller f in the way that I'm just saying, skipping some steps, but for the sake of time management, let's say, mod SL2R, these are not so important factors in this review. We have e to the c, which is a constant that now I'm going to tell you what it is. And then you have your integral over t of the Schwarzschild of the tangent of pi over beta f of tau and tau. So these that I'm denoting with these brackets are is the Schwarzschild derivative, meaning that Schwarzschild derivative f tau is expressed as the third derivative of f over the first derivative of f minus 3 over 2 f double prime f prime squared. And where c is just a constant that emerges from the boundary term and is related to the renormalized dilaton in this way. 16 pi over g. Okay, great. So our original problems becomes these quantum mechanical problems. We could try to understand the partition function semi-classically, and there we would discover that the classical solutions are just little f of tau equals tau, and we could go on and say, okay, what about fluctuations? What about, so the result of one loop, you can compute it. Yeah. Sorry, I didn't hear you. Yes, that's what I'm doing, and let's say the length of the boundary, it would be beta over epsilon, and I'm considering beta as the length of the thermal circle. Okay. And so, yeah, we could semi-classically analyze this action. We could include one-loop corrections, and what we would obtain is this result. Basically, this is straightforward computation, and you get 2 pi c over beta to the 3 halves e to the s naught plus 2 pi square c over beta. And then you can include other fluctuations and go beyond the one loop corrections, but you would discover that all of these terms disappear, and they are they vanish. And this is not by chance, because Witten, few years ago, Witten and collaborators proved that this action is actually one loop exact. So you can perform your one loop computation and obtain the exact answer at all orders in your GN expansion, the gravitational constant. And so, very nice. We have our partition functions at all loops. We can try to learn something about the spectrum of the black hole. And so what you can do you can write it in this way. And by means of an inverse Laplace transform, you can extract what's the spectrum of the theory. Okay, so let's do it. And what you obtain if you do this is the following answer. C over 2 pi e to the s naught sinh of 2 pi square root of 2c e. Okay, very nice. But the result is quite puzzling, because in the standard holographic setting, you would expect to find a sum of delta functions. You would expect a discrete spectrum, because you are basically saying that you have a two-dimensional theory of gravity, and your holographic dual should be a one-dimensional quantum mechanics that lives on a compact space. It should be a discrete spectrum. So what's going on? Where I'm going wrong? Well, actually, the point, as you spotted earlier, is that I'm just including the topology of the disk. We need something more than perturbation theory to obtain a sensible answer. And we need to include non-perturbative terms. And these non-perturbative effects are encoded in higher topologies that we should sum over in the path integral. So, for example, here for the partition function, what we should do, we should not only include the topology of a disk, but we should consider, for example, also a spacetime with this topology, spacetime with two holes with only one asymptotic boundaries, and so on. And each one of them will have a different Euler characteristic. This one is it's chi equal to 1, chi equal minus 1, and on and on and on. And each one of those will have a prefactor coming from the Einstein-Hilbert term of the action that will be basically e to the minus phi 0 over 16 pi gn, and so on and on. And so these are non-perturbative terms that we are including. Okay. Usually these terms are quite difficult to compute in a generic theory, but in JT gravity we have enough control to understand systematically how to compute each one of them. So let me demonstrate how we do it. Basically, let us consider the topology of the torus, just for the sake of doing something simple. What we do, basically, we cut this topology in two pieces. This one is a geodesic, and we are sure that we can find a geodesic which is homologous to the boundary curve here. It is a mathematical result. We can always do that when our manifold is hyperbolic. And so we cut this spacetime in two pieces. This is what we call the trumpet. It has the dynamical pieces on the boundary and a boundary which is not dynamical, which is just a geodesic. And then we have this other piece. So we can perform the same computation that we did here for the trumpet spacetime, and we would discover that this is again one loop exact. And so we know what's the expression of the trumpet. So we have the partition function of the trumpet. Basically, we path integrate over this spacetime, we get something that we know, we can compute. And then what we are left with is the path integral over the spacetime without any, let's say, dynamical boundary. What we are basically computing is an integral of this form, G mu nu, is an integral of this form over this manifold. And this is what we call the Weyl-Petersson volume. Basically, we are computing what's the volume of the space of all the possible inequivalent metrics that we can put on a topology like that, with the constraint of them being hyperbolic. So this we call, in this case, V genus 1 boundary. Okay, and once that we have all these ingredients, then we can compute this path integral basically by gluing along the geodesic these two components, genus 1 and 1 boundary. And we can do it not only for the partition function, but we can extend these results also to different type of spacetimes, and with spacetime with, let's say, n asymptotic boundaries. And yeah, you're right. B is the length of the geodesics. So you're basically integrating over all the possible lengths of the geodesics that may be here. Okay. And so if you perform this computation, let's say not for this case, but for the most generic case where you have not one asymptotic boundary, but n asymptotic boundary, what you get is basically a structure of this type. You have to sum overall your different topologies, and each one of them is weighted by its Euler characteristic plus minus n. And then you have this term right here, which is the contribution of the single one of the diagrams. And this one can be computed analogously to this one, obtaining this result. This beta 1, beta n. And here we have to glue. Okay. Integral. We have the product over n, b, the bi. And here we have the trumpets that we removed, beta I, bi, and here we have the Weyl-Petersson volume. Okay, so if we are able to compute this Weyl-Petersson volume, then we are able to exactly solve the theory also non-perturbatively. And these objects are actually quite hard to compute. Later in the talk, we will briefly mention how we could do it. But with this definition is a complete mess. Luckily, a decade ago, more or less, Mirzakhani, the mathematician, came up with some recursion relations that allow to compute systematically these Weyl-Petersson volumes by knowing the ones with less genus and less boundaries. These are very difficult recursion relations. Later I will show, but just to let you know, we can actually compute them, provided we have a computer. And so the theory is actually non-perturbatively solved. Okay, fair enough, but what about holography? Where does holography comes in this picture? Well, the inclusion of these effects actually allow us to understand what's the true holographic dual of JT gravity. And this is not simple quantum mechanics, but this is what is called a random matrix theory. So unfortunately, I will have no time to review in detail the correspondence, but what you should keep in mind basically is that inside the random matrix theory, you could try to compute the product of partition functions this type and take the ensemble average. So basically you're taking the ensemble average of something like this, beta 1 trace minus beta n h, which amounts to integrate over the space of the Hamiltonians with some probability density function of all your zetas. And what you discover is that this quantity is closely related to the decomposition that I showed you there. But how exactly they are related? Basically, inside the matrix model world, you can try to perform a large n expansion, what's called, sorry, yeah. Yeah, you're right. It was just to distinguish it from what I'm, what I'm intending when I've written. Over, let's say, inside the matrix model, you have some random variable, which is the Hamiltonian. And so the Hamiltonian that you're considering, all of these Hamiltonians are random variables. And then you have to average over the entire ensembles of Hamiltonian that you're considering. And in this case, yes. Each one of them is a particular realization of the Hamiltonian of the matrix model, and then you have to integrate and perform the ensemble average over all the possible ones with some measure. And here the measure of interest, let's say, is the one associated to what are called the unitary matrix models. So here you have just to say the van der Monde squared, let's say, of the eigenvalues. Okay, and so what actually you can observe is that these quantities are known to have a well-defined large N expansion inside the matrix model, and in particular you can, let's say, this is not an equal, but you have some sort of decomposition like that. You have zeta, let's say, let me write those in this way, although it is not precise. And here you have n, which is the dimension of the matrices, the parameter that you're expanding with respect to the minus the Euler characteristic of the manifold you have to embed your 't double line expansion diagram into. What you discover is that for these quantities, there actually exists some recursion relations to compute. And these are called topological recursions and comes in the matrix model from some Schwinger-Dyson-like relations. And what's interesting is that Saad, Shankar, Stanford, a few years ago discovered that for some, for a given type of matrix integral, actually what you can do, and you can map exactly this type of recursion relations on the Mirzakhani recursion relations. And this establishes a non-trivial correspondence among these theories. And so what you discover is that the path integral that you've written above actually corresponds to this quantity that I've written here. This correspondence, let me just mention, it's clear at the perturbative level in the matrix model, while we are matching it to some non-perturbative result in JT gravity. And so what does it mean? It means that these topological expansions that I've written down in the context of gravity is actually asymptotic. And that to be well-defined, JT gravity requires a doubly non-perturbative completion. And you could say, okay, who cares? I mean, doubly non-perturbative effects cannot be important. I mean, they are too small, but they actually aren't. There are some observables for which they are fundamental in order to understand their behavior. So I think this is a nice way to pause for a moment. If you have any question, feel free to ask. Otherwise, I'll move on and I'll tell you something about the spectral form factor. Okay, sure. Which one? This one. This expression. Okay. Yeah. Okay. So we have a product of zetas. Let's say we consider just one of them, so that we can recover the expression there. This is the expression when you all include the disk topology, and so it means that is the leading order answer that you would get by just considering the first term in this large N expansion. So you will recover this expression by looking at the first term in this large N expansion once you tune appropriately the potential of the matrix integrals in order to be dual to JT gravity. In particular, what you need to do practically is you have to select your matrix integral so that the spectral density at the, let's say, the disk level that you get here in JT gravity is the same spectral density that you get in the matrix integral in the large N limit as dominant contributions. Once you do this, then you get this equality. And this Z inside the matrix model is actually equal to what you get non-perturbatively for JT gravity. This is at the perturbative level here, but then you assume, okay, then the prediction of these matrix integrals will be the completion of the prediction of JT gravity. Right. And the non-trivial part is that it is sufficient to say, okay, I want to get the same spectral density to actually get everything to be equal. Every term in these expansions will be equal. So this is non-trivial. Okay. So what about the spectral form factor? This. Yeah, the genus expansion is asymptotic and you need to complete it in some way. Okay, so, all right. So let me tell you something about then the spectral form factor, which is one of the words that you see written there in the title. Basically, let us suppose to have one-dimensional quantum mechanics. The spectral form factor is basically defined as the product of two analytically continued partition functions in this way. And what you get by this expansion, okay, is basically something like this in the case you have a discrete spectrum in your theory. And here is e to the minus et en minus em. What should we expect for the behavior of this observable in as the time varies? Basically, what you expect is something like that. You begin here with the value of zeta of beta squared. Yeah, here I guess there is something like this, maybe. And then there is a decaying behavior, and then what you get, in case you have a discrete spectrum, as the time increases, this observable becomes sensible to the difference in the energy levels of your theory, and there is some sort of erratic behavior. This is a not very well behaved observable at late times. But in case instead you have a continuous spectrum, what you would observe is some decaying of the spectral form factor forever. So what you hope is to be able to study such an observable in a theory of gravity. And so to be able to understand this region by some sort of sum over geometries of stuff like that. But you have no hope of doing it in this sense because this is too irregular, meaning the manifolds are too smooth to reproduce such a behavior. Luckily, in JT gravity, we have some more hope because we are not considering a quantum mechanic dual, but we are considering a random matrix theory, and so there is some averaging involved. And this averaging actually smoothens out these oscillations, and you get something more regular of this sort. And this you can hope to recover inside of your theory of gravity. So this is a good place to begin using these slides. And so what you want to do, you want to try to understand this plateau behavior, which is the part of the spectral form factor which is sensible to the discreteness of the energy levels from gravity. Please. Here, if I'm talking about quantum mechanics, no, I'm just performing the product of the two zetas, the two z. But inside the random matrix models, actually, yes. What you have to do is always have some averaging over them. And so here is the definition inside the random matrix theory. We have this product. Okay. We have this product. And inside the integral, this rho is actually the joint probability density functions of the energy levels. And so we would like to reproduce this behavior from the gravitational side, but how to do it? We should try to study the, let's say, the space-time with two asymptotic boundaries, and then analytically continue them. And if we consider only the product of two disks in this expansion, so we are studying something like that in JT gravity, if we consider only the product of two disks, actually this observable always shows a decay as t to the minus 3 LA times. So there is no sign of the underlying discreteness, let's say. And so it is necessary to include also non-perturbative contribution to reproduce the correct form of this observable. And for example, this connected geometry, disconnected geometries, such as the one with the topology of the cylinder, helps us to recover the ramp contribution. This has a behavior that goes like t over 4 pi beta for late times. Okay, so you may argue, okay, so let us include higher genus topologies, so the cylinder with a hole or two holes and so on, we will be able to recover also the plateau. Well, this is wrong. This is not enough. All the other contributions, with the exception of these two, will be decaying at late times. And so there is no hope from this expansion to actually recover the correct form of the observable. And so what we need to do, basically from the gravitational standpoint, we don't know. No one knows which are the correct contribution that we should add to this expansion to recover the plateau. There are some speculations about it, but no one is sure. The picture is somewhat more clear from the matrix model side, where you can perform your numerical computations and recover the plateau, actually. And so, however, there is a particular regime in the theory of JT gravity where we can actually try to make some more analytical progress. And this is the tau scaling regime of the theory. Basically, what we do is we defined a new variable of time, which is called tau, which is basically the product of t and e to the minus s naught, and you consider a regime of late times, t goes to infinity and s naught goes to infinity, by retaining tau fixed. And what you discover is that inside the matrix model, then there is an effective, let's say, an effective joint probability density functions which has this peculiar form, which is universal, so independent of the potential of the matrix theory, and is called the sign kernel. With this expression, which becomes exact in the tau scaling limit, what we discover is that basically the spectral form factor has a nice integral representation in terms of this minimum function. And that, quite interestingly, this expression becomes analytical in tau whenever rho 0, which is the spectral density of the matrix model, is an increasing function. And so, very nice, we made a lot of analytical progress. So what can we learn from this, from the gravitational side? Well, first of all, let me point out, let me hide this, okay. First of all, let me point out that not only this expansion is convergent and not asymptotic, but we can also understand each one of the coefficients of these expansions. And we have a closed integral form for each one of them once you provide us with the rho 0, the spectral density of the matrix integral. So, okay, very nice, but what about the gravitational side? Actually, this expansion looks like the topological expansion from the gravitational side, because once you recall what is tau, tau is t e to the minus s naught, all those terms closely resembles the, let's say, the contributions of the topologies in the gravitational expansion with higher and higher genus. And this is exactly what you get. Actually, you can understand the plateau in this regime directly from the sum over the gravitational topologies. For example, in the case of JT gravity, once we insert this spectral density inside the integral representation, what you get is some expansion like this, and the linear term you already know that comes from the cylinder topology. The cubic term will come in the tau scaling limit from the cylinder with a hole. The term tau to the fifth will come from the term with the cylinder with 2 holes, and so on. Each one of these terms will come directly from the sum over topology with no need of doubling non-perturbative contributions. So, very nice. We have some perturbative access to the plateau. And so we wondered, what about these contributions in the supersymmetric generalization of JT gravity? What happens if we add some fermions to the bulk? Does this structure still holds? Well, first of all, what we need to do is to add some fields of spin 1/2 and spin 2/2. And the story is pretty similar to what I've just told you. Instead of this version, what happens is that you have your supersymmetric generalization, and the spectral density of the theory you can still compute because the partition function is one loop exact, and you get this expression, which is again continuous, but now you know what you should do. You should add higher topologies to explain in an orographic context what we are learning. And once again, what you discover is that you have some sort of duality to a random matrix theory. This one is called chiral Gaussian unitary matrix model, which is basically a unitary matrix model as the one that I've presented you before, but with the constraint of eigenvalues being positive because of supersymmetry, basically. The main difference in the spectral density is that it features an hard wall when we approach small energy. Basically, we have a divergence as 1 over square root of E near the edge. Okay, so we could try to analyze the spectral form factor in this theory. What do we get? Well, in the tau scaling limit, first of all, we have to make sure that the sign kernel still holds, so that we can actually have the spectral form factor expressed as this nice integral with the minimum. And this actually what we observed. Indeed, far from the potential, far from the wall, we have a unitary matrix model where the sign kernel holds. And then when you get near to the barrier, you discover that the kernel is actually the Bessel kernel to be considered, but in the tau scaling limit, it can be proved that it reduces to the sign kernel. And so, okay, very nice. So we can still use the integral representation that we used before for the spectral form factor. Well, basically everything is the same. We will get a convergent expression and we are all happy. Well, actually, no. If you try to perform the same computations that we did before, what you would discover is that the every coefficient of the perturbative series in tau that you're considering is now 0. And this is basically because of the fact that the function which is inside of the integral has no poles around the origin. And so this is a quite peculiar result, but this is actually correct. And we verified it even through a bulk computations. By performing the sum over geometries and the supersymmetric setting, we discovered that all the geometries with genus higher than this cylinder actually give us 0 contribution to this sum. And this is because of the structure of the super Weyl-Petersson volumes that we would need to compute this type of contributions. Okay, and so what it actually means is that since we expect the plateau to emerge, because in the function with the minimum, the representation with the minimum, we know that the spectral form factor has a plateau in the tau scaling limit, it must be induced by some non-perturbative phenomenon and some non-perturbative contribution. Okay, very nice. Usually what we do is we could try to extract them through some sort of resurgence theory, so that we can complement our original series with some non-perturbative contribution obtaining a trans series, let's say. And this is very often done in this context, for example, through resurgence theory. So let me first remind you how resurgence theory works and how we will work in our setting. Well, usually what you have in resurgence, you start from an asymptotic series with coefficients being factorially divergent. And then what you do is you define a new series, the Borel transform of the original one, that you obtain by removing the asymptotic, the factorial growing, let's say the factorial growth. And then you defined a completion to your original series by means of a directional Laplace transform of the Borel transform. And in this context, the non-perturbative physics is basically hidden in the singularities that you find in the Borel plane. So for example, let's say that you have a pole or a branch cut located on the real axis of your Borel plane. How would you extract your non-perturbative informations? Well, you would get some ambiguities in deciding whether you're performing your directional Laplace transform above or below your cut. And the non-perturbative contributions are encoded in the discontinuity of the result that you would get by performing one or the other. Okay, very nice. So the idea is clear, but what about our theory? Well, actually we have a problem because our perturbative expansions truncates actually is made only of one term. So we cannot even start to perform such resurgent analysis. Yes, that's true, but this is where the Cheshire cut resurgence comes in. Basically, the idea is that our perturbative series truncates because we are on some unfortunate point on the parameter space of our theory. Basically, we expect that by moving away from this peculiar point, our perturbative series would reappear. We could perform the resurgence program on it, and then at the end, once we have the non-perturbative result, we can turn the deformation off and read the result for our unperturbed theory, our physical theory. And this is actually what happens. And the Cheshire cat parameter, in our case, we discovered being the genus of the surfaces that we are considering. We are considering clearly the genus that of the surface is a natural number, but if you deform it to be a real parameter, then you would discover that actually your perturbative series reappears. And not only it reappears, but it has some factorial growth on its coefficient, as you can see. These are the coefficients that you would get by deforming the genus in genus plus a small real number. And of course, in front of everything, you have this sign of pi epsilon, which says that the unperturbed theory has vanishing perturbative series. Okay, very nice. We get this complicated expression, but now we can perform resurgence. And this is actually what we did. And the only other thing to mind is how to fix, let's say, the Stokes coefficient, meaning, okay, so we extract by means of the discontinuity the non-perturbative answer, but what is the multiplicative constant that we should add in order to obtain the sensible non-perturbative completion to our original theory? Well, this can be fixed, and we did it by comparison to the low energy limit of our theory, which is analytically tractable and for which we know the result. Okay. Once you do that, what you discover is that the spectral form factor reappears and its non-perturbative completion resurges and has this form. Basically, the first term is the only one that was present. It was this tau over 4 pi beta, and all the others are new terms that allow you to recover, once you include more and more contributions from this sum at the end, the correct form of the plateau. Here in the graph, what you see, you can see let's say, the dots are the numerical evaluation of the spectral form factor, while the dashed line is the result that you would get from the result above without including any term in the last sum. And once you add more and more terms, you see that when you arrive at including 5 terms, you have a pretty good agreement with the numerical result you expect. And what are those terms? These z, n are actually polynomials that you can explicitly compute, and we did it so you can add whichever number you like. So to have a more quantitative comparison, here what I'm plotting is the logarithm of the relative error between the numerical result and our analytical result. And as you can see, once you arrive at including 5 terms, you have in the region of the plateau an agreement which is with an error of around 10 to the minus 14 or stuff like that. So a pretty good agreement. And here are some polynomials that you can consider. And the point is that these contributions that we were able to extract are actually the first contribution of this type that you can analytically that were analytically extracted, because usually this observable is studied by means of numerical analysis. And so we could try to understand better gravitationally what are these contributions. These are most likely contributions coming from disconnected geometries, but the analysis is still ongoing. So this is the first part of the talk, so let me stop for a moment if there is any questions. Otherwise, please. Right. Okay, this is an excellent question. The true answer is that I don't know, meaning that there is clearly some pattern, and we were able to extract a part of it, but we were not able to, let's say, understand completely why there are these type of fractions. So it would be very interesting to understand, but for the moment we don't know. Yeah, they are. No, I mean, no. We didn't prove it, but we could definitely have a closer look at that. Okay. No, thank you for the question. No, there is actually a closed formula for the computation of these polynomials. They are very length formulas, but you can give me whatever number of, let's say, whatever n you would like me to compute you for these polynomials, and I'll give you the answer in a few moments with Mathematica. No, I mean, it is not that it is not clear, but we didn't investigate it deeply. So probably it might be, but we didn't have a look. So yeah, we included the red curve is the result of our analytical expression once we include only three terms from the sum. This is yes. Yeah, meaning that we computed the spectral form factor with the integral formula that holds when the sign kernel holds inside the matrix model. So in the tau scaling limit, it is the spectral form factor in the tau scaling limit. Right? I mean, actually, the integral representation of the spectral form factor that we are using is tightly bound to the fact that the correct kernel to use is the sign kernel. The Bessel kernel, well, actually, what we did is we verified both numerically and analytically that the Bessel kernel in the tau scaling limit strict converges, let's say, to the sign kernel. So we are pretty confident that in the tau scaling limit, this is the correct expression we should get for the spectral form factor. Okay. Okay. So if there's no any other question, let me move on to the second part of the talk, which is a bit more, let's say, mathematically flavored, meaning that we'll be talking about Weyl-Petersson volumes. And so, okay. So let me denote with this VGN, the volume of the moduli space of Riemann surfaces with genus G and n geodesic boundaries. Basically, what I'm saying is we will talk about this volume here, which previously I introduced using the path integral. They actually have an algebraic geometry definition that we will not need, but I included here for reference, and it can be, they can be computed through this integral over the moduli space of Riemann surfaces of some cohomology classes, this K and this psi. But what matters about this formula for us is basically the fact that these polynomials might be very complicated functions, but they are actually, these volumes might be very complicated functions, but they are actually not. They are polynomials. Polynomials in the length of the boundaries of our Riemann surfaces. And they have, in this case, degree 3g minus 3 plus n. And as I told you before, they are pretty difficult to compute from scratch, but Mirzakhani discovered that they satisfy a set of integral recursion relations that allow for their computation. And they are those right here. So as you can imagine, by looking at them, these D are some kernel functions that I did not report here for this case, but that I will show you for the supersymmetric generalization that we will care about. But in principle, by using these relations, you can compute whatever volume you like. But there is no closed form expression for them. You have to resort to this type of stuff. And so they come with some supersymmetric generalization that was introduced by Witten and Stanford when they discovered, let's say, or invented this supersymmetric generalization of JT gravity. And they also come with some mathematical definition in terms of integrals on the moduli space. And they, again, are polynomials. And they have a different degree from the others, degree g minus 1, and satisfy analogous recursion relations to Mirzakhani's, and can be computed using this kernel. So, as I was saying before, no closed form expression is known for them, so mathematicians thought that it would be interesting at least to study their expressions asymptotically as the genus increases, where it is more, let's say, easy to understand their structure. So what's the state of the art? The state of the art is basically that many papers were written on their asymptotic expression, and I've written down a few of them here, but there are some seminal works by Mirzakhani herself, or Zograth also, for the standard bosonic case, and these are the asymptotic formulas. They are divergent as 2g factorial, but as you can see from the product of hyperbolic science on the right-hand side, these asymptotic formulas do not respect the polynomial structure that we have on the left-hand side. This is not a problem in its own, meaning they are good asymptotic formulas, but if you want to use this expression in some integrals, such as the ones that I showed you there, the exponential behavior of these sine functions, I mean, they are not so good. You have to be very careful while using them. For the supersymmetric case, instead much less is known, and it only exists a formula proposed by Witten and Stanford with this integral representation in the case of one single asymptotic boundary. So what I'm gonna do now is to present you some new formulas that generalize this Witten conjecture to the case of n asymptotic boundaries, and that respect the polynomial structure of the volumes, as Witten's formula does. Indeed, if you were to evaluate this integral, you would discover a polynomial of the correct degree, and so with the correct structure. So first of all, the formulas that we propose are these ones. They are basically very similar to Witten's one, and they reproduce its formulas in the case n equal to 1. And they are actually polynomials. Here I've reported two formulas, meaning that the first one is the leading order in this large genus expansion, and the second one is the first subleading contributions, let's say, that there is some sort of a hierarchy of contributions, and these are the first two that we propose. And they both produce polynomials in the length squared of the correct degree, respecting the functional form of the Weyl-Petersson supervolumes. And actually, we can also obtain some formulas with the hyperbolic sign, but you recover them only in the regime of the genuses being much greater than the length of the boundary of the volumes. And here you can perform the integral by saddle point analysis, and you will get something like this. But our formulas are actually valid in a wider range, let's say. So let me convince you of the validity of these formulas by showing you some numerical evidences. Actually, what we did is computing exactly those integrals and obtaining the expression of the single coefficients of the monomials that made up the polynomials. And here is their form in terms of generalized Bernoulli polynomials and other simpler functions. Okay, and so what we did to compare our result with the true result of the volumes is we defined this ratio R to be the ratio between the coefficients of our proposed polynomial to the coefficient of the true polynomial. And we took the worst of these ratios, meaning the one that is farthest from 1, and we plotted here in the graph. The green dots are the results for the, let's say, the leading order asymptotics that we proposed, and the blue dots for the first correction added. And what we discover is that as genus comes to, let's say, 20, we have 1% error in the case of the first asymptotic formula, and 10 times better for the case of the second one. But they actually perform quite well even at low genuses. And so, just to show you another graph, here instead I plotted the ratio between the Weyl-Petersson supervolume with two boundaries and our proposed asymptotics. The full lines are actually these ratios, while the dashed lines are the ratios when you use not the formula that respect the polynomial nature of the volumes, but the one with the sinh functions. And so what you discover, as you might have imagined, our formula is much more stable than the others. So, okay, very nice. But how did we get this result, and where resurgence come from? So let me briefly tell you this, and I'll finish here on the blackboard. The idea is to start from these ansatz for the asymptotic of the volumes with some unknown coefficient here, dz over z, 1 over sine 2 pi z to the 2g minus 2 plus n. And here the product of the sinh BEZ over BE. And then, which we now will try to motivate, and then we basically use some relation that are known amongst these polynomials, which is this one that was proved by Norbury, which relates the polynomials with n plus 1 boundaries. One, you can analytically continue one of them to complex values. Basically, using these relations, we were able to obtain some recursion relations for these coefficients, and by using the result by Witten, we were able to extract the correct coefficient that we showed. But so the question is now, how to obtain these ansatz? Well, the answer is resurgence theory. And so I've already presented you something about resurgence, where you start from an asymptotic series and then you perform the Borel transform and you can obtain well-defined non-perturbative results. Now we'll go the other way around. meaning that our strategy will be to find a physical theory where these polynomials enter in the perturbation theory, trying to understand somehow the perturbative completion and then go back and understand from the completion what's the behavior of this asymptotic series. And how should we do it? Well, I showed you before that when you have a perturbative series, something like that, with a k factorially divergent, what you do is you define a Borel transform in this way. And then, basically, you define the completion of your original theory by means of some sort of integral like this. Well, once you have something like this, actually you can go back. If you have some sort of expression like this, somehow, you can read your Borel transform, and knowing your Borel transform, then you can know your coefficients. And this is pretty obvious. It's just an application of Cauchy theorem. Basically, AK is gamma to the k, sorry, gamma of k over 2 pi I, the integral, the t Borel transform over t to the k. So we already know how to do it, basically, because we know a physical theory that features these volumes in a perturbative series. This is JT supergravity. And so if by some means we were able to extract some sort of expression like this, then we could learn something using this formula. This is exactly what we did. Basically, what it is known and what was, let's say, firstly understood by Marcos Marinho and collaborators a few years ago is that basically there is a systematic way of extracting one instanton corrections to the path integrals that we are interested in. And there are some, let's say, integral formulas analogous to these from which we can extract the information we need. And now I'm just writing you down the result. And basically the point is that you compute this non-perturbative contribution to the partition function, and then you strip off your trumpets, and you get the non-perturbative contributions to the generating function of the volumes. So the generating function of the volumes, just allow me to write it like this, is obtained by stripping off the trumpets, basically. And so using the technology developed by Marinho and later last year by Gregori, Schiappa, and Arden collaborators, we were able to obtain some form for the first instanton contribution, which goes like this: e to the minus v, and some effective potential of the matrix integrals, where the effective potential simply has this form. And so now what we do, we interpret this as an integral analogous to this one, basically by performing some change of variables inside this expression, and we eventually get something that looks like this: the integral over dt e to the s naught. This is just a change of variables. If you wish, lately I can show you which is the exact change of variables that you should perform. And so sinh of b z of t over be, where z of t is, where z is this, I would say. And so from here, by comparison to this expression, we can understand that, and we can interpret at least this part of the integral as the Borel transform of our original asymptotic series. And by means of this, by means of Cauchy theorem, we can extract some prediction for these coefficients. If you do this, you exactly get the result that I show you here in the first line. And so basically by means of resurgence and by leveraging on the knowledge that we gained from some physical theory, we were able to extract some asymptotic formulas for complicated mathematical objects. So basically what I've told you today is I've introduced you to JT gravity, and I show you how resurgence theory can help us both in the physical theories, understanding the microstructure of black holes, and later how both the fields can benefit from the exchange of one another, and how resurgence can be helpful also in mathematical situations like that. So, thank you. I mean, yeah, that's an interesting question. Actually, you could start in these theories with the most general two derivative action that you can write down for the scalar. So you can add a kinetic term, you can add some coupling to the Ricci, to the curvature scalar and stuff like that. But then by just some redefinition of the fields, you would end up basically every time with an action like this one. The only difference that you could get would be to have here, instead of the 2, you could have some structure like this, let's say. This part of the action could be of this form. Phi, which is coupled to R, and then you might have some potential for phi. So JT gravity is basically the simplest choice that you can make for this potential, taking it linear. And if you take it linear, you get this one. So yeah, that's very interesting. You could do it, and then you would end up with the same action. Please. Yeah. Sorry? Right, but okay. From this function? Well, actually, you could, but let's say you already have the information because this is already the, let's say, the completion of your series. So if you get this result, you already know the information, this type of information. I mean, this is already the non-perturbative part that you would add, let's say, to your theory, from which then you can back engineer the Borel transform and stuff. But so that would be interesting, but I think that it is already encoded in these expressions, what you're asking, meaning that this is already the contribution that you would like to add to your perturbative computation, if this is what you were meaning. Not sure. Okay, thank you. Right? Mhm. Okay, those are different. There are different perturbative series that we are considering. So the one that you are referring to is a perturbative series in. Let me erase this one. It's a perturbative series in, let's say, Gn, the gravitational constant. Okay, and this is the one that when you this is the type of expansion that when you try to implement to your partition function, you get, okay, every other loop but the first one will be zero. Okay, but now there are some other sort of perturbative series that we are considering, and the ones that here play a major role are perturbative series in this parameter, which are non-perturbative in this one. And this is, let's say, the expansion that you get in the sum over topologies. This is, again, perturbative in some sense, or let's say more than perturbative, I would say this is asymptotic. And so you get some non-perturbative contributions that, again, you should add. But um, let's say if you were referring to the spectral form factor part, I guess, not sure, but uh, the the let's say you're working with this one, and so you should not expect to recover something about this other series. Yeah, right. Yeah. Okay. Okay, right. Okay, you're right. There are many different series. Okay, so this story is the one that I told you before when I was describing the partition function. But then we considered another observable, which is the spectral form factor, which, if you wish, is the partition function of a universe with two asymptotic boundaries, and then you continue analytically the length of the boundaries in this way. Okay, right. This you can compute by summing this type of geometries, and let's say with a hole and etc. Okay, right? In the tau scaling limit, and these are non-perturbative in this sense. Each one of them is proportional to, all right. Now you go to the tau scaling limit, which basically means that you define the new variable, this one, that you hold fixed while you send t and s naught to infinity. And what you discover in the supersymmetric case is that in this limit, this type of series truncates. All these contributes zero. So this is something, there is another series on top of the ones that we were considering before. And by deforming the genus of these surfaces of this series, we got some other, yeah. Completion. Right. You, right. You get back the, let's say you computed the non-perturbative result for the deformed theory. But then at the end, looking at the structure of the non-perturbative effects, you send epsilon, the deformation parameter, to zero, and you extract the correct information for this observable of the physical theory, not the deformed one. Of course, it is consistent to these ones, meaning that you see that, let me show you, okay, right? You see that the only perturbative term in tau is this one, which is the linear one coming from the cylinder. All the other stuff is, let's say, non-analytical in tau, so you cannot see them. Right, you cannot see them in an expansion around t equals 0. Please. Right. Right. Sorry, we have this term, but then? I mean, you mean when you sum over different topologies, or well, when summing over different topologies? Okay, okay. So you're asking whether or not there are some, let's say, perturbative contributions that you should do on top of this. Well, in these observables, there aren't. Meaning that if you just compute the partition function in um, the partition function of the theory with this matter content, then you only get this. Maybe if you were to add, let's say, some other scalar field in the theory, probably you could get something more interesting from this point, but I'm not completely sure. I should check. Yeah. Should I interpret this as a transasymptotic expansion? Well, uh, yes and no, meaning that um, one could, meaning that you have your, let's say, uh, instanton, and then you have on top of these some sort of series with tau. But if you have a close look at the form of this z, you see that these are polynomials not in tau over 2 beta, but in 2 beta over tau. And so we started from a series in where we have some type of expansion like this, but we get something that goes the other way around. So it is a bit peculiar, and we still have to interpret it correctly from the physical standpoint. But sure, at first glance, you could say it. Yeah, right. Uh, right, right, right. Yeah, but I mean, beta, let's say, could be the Euclidean time, meaning that you have to Vic rotate. Okay, so if now we analytically continue beta to have an imaginary part, then you could say, oh, it's kind of like going back, right? Right. Okay. Uh, right. I mean, okay. Thank you. Okay. Well, we actually try to understand the convergence or asymptoticity of this series. We try to believe, we tend to believe, let's say, that this is asymptotic. I mean, meaning that if we keep on adding more and more of these terms, at a certain point we plateau in the accuracy of the, let's say, of our result, but we were not able to prove it. So it would be interesting to understand better the structure.